Hello. So I will be talking about the effect of the impacts on atmospheric and thermal evolution of Mars. Planetary impacts are the most common surface geological feature that you see in the solar system. Almost all solar system bodies have traces of impacts. And those impacts, they have affected globally or locally the environment, change the atmospheric and thermal evolution, as well as the habitability. One example is the Chicxulub impact crater that occurred on Earth 66 million years ago and caused a major mass extinction. Mars also suffered from asteroid and comet bombardment. Currently, we have more than 600,000 craters on Mars. Compared to 600,000 on the Earth, we have only 180 impact craters. Mars, of course, kept a record of this bombardment. And among those 600, about 400 they are impact craters with diameters larger than a kilometer. We have also very large impact structures with diameters larger than 150 kilometers. Those are the impact basins that occur during the Noachian. To date, the craters that we see on Mars, we have to use chronology. One of the models that we can use is based on the crater counts of lunar surface units with known ages. This is the standard model given by Hartmann and Newcomb on the left-hand side. Note that in these models, especially this part, we lack the information because we don't have the records of early cratering structures on the Moon or in other solar system objects. And another alternative that we can use for the chronology is to use a dynamic orbital evolution of the solar system. And this is what we have heard yesterday and today, and it includes the migration of the gaseous giants in the solar system. And this gives a sudden increase in the impact rate about 4 billion years ago. As I said, in early part of the solar system history, we have no records of impact structures. But we know that, for example, large impacts occurred. Those are the impacts that caused by planetesimal that are the leftovers of the creation. One of the impact, for example, created the Moon on the Earth, an impact on the Earth that created on the Moon. A similar one could have occurred on Mars that caused a hemispheric dichotomy. This dichotomy actually is the crustal thickness between northern and the southern hemisphere of Mars. And so a large impact that took away almost half of the planet. And this is, of course, a theoretical suggestion, hypothesis. And there are also other hypotheses for this hemispheric dichotomy. What we know is that there are large impact basins. These are not as big as this mega impact that I just mentioned, but these are quite big, ranging from 1,000 kilometers to 3,400 kilometers, and they are all formed between 4.1 and 4.2 billion years ago. Note that we don't know exactly those dates. Knowing the dates of these basins actually have implications, especially on the migration of the gaseous planets and the solar system formation. Such big events cause global scale changes in the fluid patterns in the mantle and can cause actually below the impact an upwelling and resulting long-lived convections. And imagine several large impacts that occurs on Mars one after each other in a short period of time. Then they can change completely the heat flow at the core mantle boundary, and also has an effect on the global magnetic field and can cause even the shutdown of the dynamo. Smaller impacts, they have, of course, smaller effects. These are the simulations on Venus done by Cedric. But they can last maybe 10,000 years, and they don't really change too much the mantle structure. The large impacts, about 100 kilometers and above, they have a long-lived convectant patterns that can also trigger volcanisms, outgassing. It may generate greenhouse effects. and affect the atmospheric evolution. If you look at the chronology of Mars, what we have been talking, the magnetic field and large impacts, they occur relatively early. There's also volcanism. That's coincidence with the formation of the large basins. And we have also the activity of the water, especially on the surface. The water activity, of course, as we move on from Noachian to Hesperian, diminished. It became episodic, and today it almost disappeared. This water activity, of course, is associated with valley networks and the alteration of the surface. It's also interesting to compare this chronology with the Earth, especially the boundary between Noachian and Hesperian, where we see the water activity, the changes in the Martian climate to the Earth. About this time, we start to see the first living organisms. When we go back to Mars, at the border between Noachian and Hesperian, so as I said, there is evidence suggesting the stable liquid on the surface, which implies actually a higher atmospheric mass. We know that it's not easy to remove an atmospheric mass. So if Mars, for example, had a 1 bar atmosphere about that time, how will you remove it? Thermal and non-thermal escape, as well as the absence of a magnetic field, they do not really affect the atmospheric escape. So impacts has been suggested as a possible mechanisms to erode the Martian atmosphere. So we can see if, for example, the last 3.94 billion years can impacts be a factor to remove the Martian atmosphere. In order to do that, we have to take into consideration different impactor types, like asteroids, short period and long period comets, and just look what they deliver and what they cause as an escape. For that, we have to take into consideration for each impactor the velocity and mass distribution, as well as the impact flux. The difficulty, or the challenging part, is to look at for each single impact the erosion efficiency and volatiles delivered. This can be done with the help of hydrocodes. These are developed for highly dynamical events. They take into consideration equation of states as well as material properties. Here I show simulations from Sweatso, a 30 kilometer stony impactor on Mars. You see that the effects are global on Mars. This 30 kilometers. You can imagine an impactor with 100 kilometers or 200 kilometers. Of course, when you add the atmosphere to hydrocode, you increase the complexity of the problem. You have to take into considerations the compression and jetting of the gas during the entry. Also, the shock wave caused by the plume of vaporized impactor and target material. These are the two most important physical parameters that you have to take into consideration. If the impacts are very large, then the free surface motion and the interactions of the high-speed ejector fragments with the atmosphere, they become an important parameters also. Considering the complexity of the problem, it's probably not surprising to see that for a given impactor diameter, the escape mass that may vary 1 or 2 order, even more magnitudes between different models. Note that this axis is given in logarithmic scale. Then we can add this information in the equation that I showed and look for different models what they can remove or bring to the Mars. And as I say, there are differences, order of magnitude differences between different models. What we can do is just to study on the case of the Mars. We know that today we are here with 7 millibar of atmosphere. If we use the most, let's say, favorable conditions for the atmospheric escape, what will be the maximum pressure that you will get at the end of Noachian? The study suggests not more than a couple of 100 millibars, which is not, of course, sufficient to have a wet climate on early Mars. The story can change, of course, if you consider the carbonates, that most of the CO2 atmosphere may be is under the surface, but we have no evidence, and this is highly debated, so I wouldn't consider that one now. The particularity of the Mars is that the subsurface we have ice, and that changes the impact, the impact process. It adds vapor, more vapor to the atmosphere, and can affect local and global climate. So one possible mechanism to create wet environment, not maybe stable, but episodically, and this is a large impact on Mars that can mobilize the water under the surface and the poles. This has been studied by several authors. It seems that you can create a steam atmosphere and greenhouse effect that can enhance the rains and create a wet climate from several years up to maybe 10 or 50 years. So this is an episodic part. It's interesting that this also coincides in terms of timing with the formation of Martian valley networks. In smaller and local environmental effects of the impacts, you can consider the formation of, after an impact, the formation of a layer with liquid water that can be sustained there, and hydrothermal systems which alter actually the chemistry and mineralogy of the surface. Those are the images taken from CRISP showing the excavated and impact-induced hydrated silicates. Just to conclude, large impacts occurred in the history of the Mars. The very early impacts could have caused the dichotomy, also caused a stop of the dynamo. The impacts later on wouldn't have too much effect on the atmospheric evolution in terms of the mass. They couldn't really erode the atmosphere, but they could temporarily alter the climate, causing episodic rain. And maybe it's most interesting to the hydrothermal systems, which may already exist in a dry and cold climate of Mars, like we have today, may allow interaction of the hot rocks with the ground ice and provide an environment where you can have water, heat, chemicals, and nutrients for extended period of time. Thank you.